So, for the time being, so I am going to assume that we will do linear parameterization. So, people have a proper visualization in mind when I am talking about this error surface and other things, right. When talking about error surface, I am talking about this gradient descent on the error surface and things like that, right. What is going to be my x axis? What is going to be my y axis? So, suppose I draw a picture like this, right, and I say I am going to find the lowest point on the error function, right. What is my x axis? What is my y axis? This is actually theta, right, and this is error for theta, right. So, remember that, right, when I am talking about functions, right, when I am talking about function approximations and looking at the response of a function to this, I will be talking about the xy space, whatever is my input space, right, and then I will have a response to the function so on so. But I am talking about error, okay, I am talking about a space where it is defined on theta, okay. It might sound like a very simple stupid thing to tell you, but the number of times people get completely thoroughly confused about this is innumerable. So, let us get that out of the way and talk about linear parameterization, right. So, I am going to assume that my state S, some state S is going to be represented by a set of attributes or features, right. So, my state S will be represented by some k features, phi 1, phi 2 up to phi k. So, what are these features? Depends, I mean depends on the problem and so on and so forth, like I was telling you earlier. So, if you are thinking of some kind of a robotics task, it could be very well that it is, phi 1 is the x coordinate, phi 2 is the y coordinate, or phi 1 is joint angle 1, phi 2 is joint angle 2, phi 3 is joint angle 3 and so on and so forth. It could be a whole combination of this. Or if you think about say backgammon, right, phi 1 could be how many coins are there in position 1, phi 2 could be how many coins are there in position 2 and so on and so forth, right. Remember, so what is k in the backgammon case? Do you remember I told you that? 192, okay, it is a very famous number. Nobody knows what those 192 features are except Jerry Tesoro. So, no, IBM actually has kept it as a proprietary thing. So, he was never allowed to, he has written about one or some features, but he is never allowed to publish all the 192 features anyway. So, the k can be rather large, right. So, even if you think of let us say a grid world, right. So, I can actually make my k x coordinate, y coordinate, right, and how many robots are to the left of me, right. So, how many obstacles are there to the right of me, I can change it into any way I want, right. So, for example, here is a representation for, that is a grid world, right, and there are some obstacles here, right. So, I can choose to represent the grid world as the x coordinate and the y coordinate, or I can say wherever I am standing, is there obstacle above me, is there obstacle below me, is there obstacle to the left, is there obstacle to the right. Now, I made it into a 4-dimensional representation. So, phi 1 will be 1 whenever there is an obstacle above me, right. So, for example, if I am here, right, that will be 2 comma 2, right. So, the location will be 2 comma 2, or so one state representation is 2 comma 2, another representation is to say going clockwise from above, right. There is nothing above, there is something to the right, there is something below and nothing to the left. So, this is another state representation, right. So, once I start moving into this kind of a domain, right. So, where I am saying it is some vector phi 1 to phi k that represents the state, I can take any problem, I can take any MDP, any description that is given to me and think of different ways in which I can encode this, right. And what is the right encoding you should be using? Depends, right. I mean, this truly depends. It is one of those things which there is really no right answer, right. So, you have to depends on what your problem domain is, right. I mean there are some mathematically desirable qualities for this phi 1 to phi k, right. What are the mathematically desirable qualities? Come on, regression, linear regression. As soon as you say linear parameterization, we are going to linear regression. So, what would I want of those k features? Linearly independent, right. So, I would expect them to be linearly independent. Okay, just because you finished one course last semester does not mean you have to forget all about it, right. So, that is a basic course, you will be using it again and again and again and again. So, it is not something new I am asking you about, okay. That is why I said mathematically desirable quality, which is it has to be linearly independent, okay. And I am sure that some of the guys who did not do RL at least when ML were in PR, right. So, between the two courses you should have known all of this by now. Anyway, so when I say linearly independent, here is another thing. So, what am I asking to be linearly independent? Values of the features. What do you mean by saying values of the features are linearly independent? Linearly, I am talking about vectors here, right. I am talking about linearly independent vectors. So, what are these vectors I am talking about? Exactly, all the observations of phi 1, all the observations of phi 2 and so on and so forth, right. So, I have S, right, but basically I have S1, S2, S3 all the way up till some Sm, right, I have M states. So, if I can write them one below the other, right, and take the first column, that is the phi 1 vector, take the second column, that is the phi 2 vector. So, I want these phi 1, phi 2, phi 3 all the way to this k, these k vectors I want them to be linearly independent, make sense? Great. But that is only if I want all this linear regression business, right. So, if I want to let us say use regression trees, right. So, what happens if the features are not linearly independent when I am using regression trees? If you remember way back when we started the class, I said this is the only chapter where I will be using ideas from ML, right. So, this is one chapter which you would find a little hard if you do not have a strong background in machine learning, but that is why I am going slow, right. In fact, it looks like I cannot assume that even the people who did the ML course have background in machine learning, but that is another issue. So, people remember regression trees? No? Yes or no? Okay. Huh? Yeah. So, what would happen if my features are linearly dependent in the regression tree?
Clearly separable regions.
Huh? What? Unlike linear regression, having linearly dependent features in trees will not be catastrophic, right. So, there might be multiple features which give you the same split value, right. You choose one of them and split, and the rest of the features become redundant, but you will still be carrying them around, but usually they will not give you a good split value once you split on one of those linearly dependent variables. So, it does not matter, right. It just you will be doing additional work, but the stability or the correctness of the solution and all of those things do not matter. So, this linear dependence essentially matters only if you are solving it using either some kind of gradient computations, right, or the more numerically intensive methods, right. So, you can throw a lot of features at it, right, and it can still hope it will work, right. Anyway. So, I can summarize this as phi of s. So, when I say phi of s, it is essentially the whole vector phi evaluated at state s, right. If I want to do that, what is that? So, the first column evaluated on the entire, it is a vector, right, phi 1 is a vector. So, the first phi 1, capital phi 1 is small phi 1 evaluated on each and every state, okay. If at all I need to use this, I will use this notation. So, capital phi 1 is a vector where the feature phi 1 is evaluated on the entire state space, capital phi of s is a vector comprising of phi 1 to phi k evaluated on s, okay. So, what is the dimension of capital phi of s? What is the dimension of phi 1? M, where M is the number of states, okay. So, just keep things straight, and that will help us. So, V hat of okay. So, that is a linear parameterization. Okay. So, I can take V hat there and plug it in here, right. So, what will I get? Now, here is a sleight of hand that I am going to do, right. I am just going to treat this as target minus current estimate, and when I take the gradient I will take the gradient of the current estimate only, right. I will not take the gradient of the target. Okay. I mean, assuming the target is coming from somewhere else, right. If this had been GT, if the target had been GT like this, that is a perfectly valid thing to do, right. But in this case what is going to happen for the linear case? Anything else? Something else?
Shouldn't that be 5 over there and not V?
Huh? Oh, this is fine. You are getting there. So, I have evaluated the gradient, right. So, the gradient of V hat will essentially be phi. Minus phi, and that is why that became a plus there. Okay. So, remember that that is a vector equation, I mean it is a set of equations. So, it will be theta t plus 1 equal to theta t plus 1 t1, so on and so forth, right. So, the first component of theta t plus 1 is equal to the first component of theta t plus alpha times the error times phi of phi 1 of s, right. Likewise, theta 2 will get updated with the same error times phi 2 of s, and so on and so forth. This is actually a set of equations written there, right. And what is this? TD error, right. So, I can essentially write this out as more compactly everyone on board? Great. So, now there are two things that we can do from here. One, we can talk about specific forms of linear function approximators, which essentially would mean different choices for phi, phi of ST. For different choices or phi, right. So, when you say I am talking about different linear parameterizations, right, essentially means different choices of phi, right. So, there are many ways in which you can choose phi, and each one deals a different kind of function approximator. So, the most popular is to just have some kind of arbitrary function like this, but then there are some very structured forms we can choose for phi, which gives us different kinds of function approximators. One thing is to explore that. The second thing is to talk about the use of eligibility traces basically the backward view of TD lambda when you are using functional approximation. Okay, these are two things that we need to do next.